Hey everybody, how's it going? So we're just getting a few things set up here, but we have our first guest ever on the Invoke RE live stream here. So very exciting first inaugural live stream with a guest. Very fortunate to have Xusheng from Vector 35 here, who is on the Binary Ninja development team, who has been working on some really interesting time travel debugging functionality in Binary Ninja that we're going to check out today. And Xusheng, do you want to introduce yourself?
Yeah, so hi Josh, hi viewers, and I'm really honored to be here. As he said, I'm a developer of Binary Ninja, and I have a primary focus on the debugger. And also, I'm a strong advocate for the time travel debugging technology, which we call TTD, and it's also the subject of this stream. So we will be showing some of the cool things we can already do right now, and I can also share some of the things I plan to build maybe over the next couple of months or the year, which can supercharge TTD and make it even cooler.
Yeah, so just for some background, I was at Reavers in Orlando and I met Xusheng in person, and he was doing a bunch of demos at the Binary Ninja booth. So they had like a vendor booth area, and Xusheng showed me the time travel debugging stuff first there. So I started checking it out myself, and we'll be going over a few examples today. What I'm most excited for is its ability to help with things like anti-analysis and unpacking, and basically anything that you would need debugging for. Once you have a capture, then you can basically go through it as many times as you want. You don't have to keep restoring a snapshot. You don't have to like do all these things that you usually have to do with a debugger. So the time travel debugging stuff is pretty promising. So I mentioned to Xusheng that I already had installed the time travel debugging stuff, but I'm just going to show you all how to do that because it is pretty straightforward. So they've set up basically this one-click install where you can go to debugger and then install windebug/ttd. And this will actually install this headlessly, and it does it all for you. So I did that in this instance and everything just worked. So super cool there.
So this works on a paid license. So if you, I don't know whether any of the viewers are using a free version, but if you are, then this unfortunately does not work. And also, I want to point out that this is not a intentional limitation. It's not like we are trying to push people to pay for a license just for this tiny feature. It's actually a bug in our code base that prevents it working from properly. So if you are using a free license, or if you are working for a really secret company like something big names, and maybe your machine is not connected to the internet, check out our docs for how to install it offline. This can all be done offline. So yeah.
Cool. Yeah, that's awesome. Yes, another thing I did, I don't know if there's plans to adjust this at all, but I noticed with the Windebug install, it didn't have symbols. So like I pulled those symbols separately just because I didn't have the NTDLL symbols. So then I couldn't do some of the Windebug stuff that I'm going to demo, but maybe something to think about in the future. But yeah, everything else just works really great out of the box. So and then one of the big limitations that I've seen with Windebug, most of you who have probably tried out Windebug have seen this too, is that their disassembler isn't very good. So this is basically a bridge between Binary Ninja and Windebug. So what's super cool about that is you can leverage all of the powerful functionality that Windebug has, but also use the Binary Ninja disassembler and high-level intermediate language or decompiler interfaces or any of the or medium-level IL or LLIL while you're debugging in order to visualize and interpret and assess what code you're looking at while you're doing it. So I think this kind of bridge where you guys have taken the power of an existing debugger like Windebug and then integrated it into Binary Ninja is probably a better approach than some other companies that have basically built their own debugger from scratch because why reinvent the wheel when you don't have to, in my opinion. So okay, so let's do a trace. So I have like a really basic example program that we can mess around with to start this off. So this is from the Introduction to Malware Binary Triage course. So we do like a malware analysis training. Xusheng also has access to that. But this is just a really basic program that I'm going to show you all first. So let's just open a command prompt here. And then this is just like the intro sample here. I'm just going to execute this from the command line. I'm going to make this font a little bit bigger so you all can see it.
Oh, I didn't know you can change the font of this command prompt.
Yeah. Yeah, it's kind of a bunch of clicks, but you can do it. Okay, so
I mean, I do it on Linux, but I have never done that on Windows.
yeah. Okay, so I'm going to run this. Basically, this is a super basic program that we use to teach static analysis and debugging. But basically, you can just say like test, and then it'll say hello test. And then there's a little Easter egg in this program that you basically have to find in the course. So I thought we could just take a trace of this with Binary Ninja and then look at this in Time Travel Debugging just as a really basic example to start with. Does that sound okay?
Mm-hmm.
Okay, cool. So let's do that. So I'll just do debugger and then do record TTD trace. And then I'm going to just go to that same directory and then select that executable. And then we'll just do the same working directory, no command line arguments. And then we're just going to put the trace in the same direction. I'll make a new folder because I think I already have a trace in there. TTD trace. Okay. And then if I hit record, then this is going to start the TTD process. And then we get the same prompt here. So if I make this font a little bit bigger, and then we put in, I think it's like 10 entries in a loop or something. Then the TTD trace recording has completed and you can now debug the trace. So now that that's done, basically all you have to do is go to debugger and then, or wait, I need to open the sample first. So I'm going to open the sample in Binary Ninja, and then let's go to our debugger and then debugger adapter settings. And then we don't want to execute, like say, okay, so like the best example of why you would want to do this is say record a trace within a controlled environment in which you don't want to execute malware elsewhere. And then you could bring this trace back into your, I don't know, lab environment where you want to analyze the debug trace and then look at it closer. So say we did that on a separate machine, we could actually just take that trace and put it on a separate machine if we wanted to, but we're doing this all on the same machine, just for example, demo purposes. But if I go to debug adapter, debug eng TTD, then I can select the trace path. And then this is our new trace here. Click open. And then all of that's set up now in our debug adapter settings. And then I can just go to launch, right? Is that correct?
Yeah. Yes.
Okay, perfect. So I'll go to launch. It gives me the same settings. I'll click accept. And then now we're actually debugging the trace. So I don't know what the security alert is for. It's probably for it's my man in the middle stuff for the malware, but that's okay. Okay, so now this is actually debugging the trace that we're looking at. So if we look at some of the windows here that I've just opened up for the Binary Ninja debugger, we have the register layouts on the left-hand side. We have values. We have the labels that correspond to those addresses. So for example, the start function or the address of entry point is within ECX right now. So then we see that there. We can see a list of breakpoints. So if we set breakpoints, we can see them there. Okay, so then we have the target. And can you explain what the target window is and how it differs from the debugger window or the
So
debugger
target. So the target console actually does not really work on Windows. It actually works for on Linux and macOS, which is basically a terminal attached to the running process. So if you run let's say if you are on macOS and you run a terminal executable, then all of the things will be showing up in the target, and you can type inputs into that in target. But on Windows it doesn't work because a terminal application on Windows always runs on its own command prompt window, so that doesn't actually work. So the debugger console, if you switch to that, you can already see some of the familiar WinDebug output that you have probably seen before if you are a WinDebug user. And you can actually just type in whatever WinDebug commands into that. So if you type the command to show registers, you can see all of the registers if you know that command.
Yes, it's R, right? Or
I can't
I use
remember.
R.
Yeah, okay, yeah.
And then I don't know if my symbols are set up properly, but you can do like bang address. Okay, let me dot sympath.
You can also
This
just show the PE as a very simple example.
load enable load checksum mapping. I don't know why that didn't work. Peb regions, bang peb. Okay, yeah, so like
Oh,
for example, like if we wanted to get the process environment block for this trace, then I can do like bang peb, and then it'll actually give me the output and like all loaded modules and whatever. So yeah, you can WinDebug is super powerful. Like I've done a previous nothing with Invoke, but I did a video. If you literally search like WinDebug basics or something on YouTube, it'll probably come up with the video that I did with Sergey from OA Labs, and we kind of just go over how to use it. But yeah, anyways,
yeah, and I
uh,
can see a funny thing in the tab is being debugged is null. It's because the tracer traces the target in a way that is not actually debugging the target. So most of the, like, let's say the simpler anti-debugging tricks wouldn't actually work against TTD recording. So you get a free anti-debugging as well.
nice. Yeah, that's even better. XOR Volok said, "Can you trace using WinDebug and then open the trace in Binary Ninja on Linux?" Can you?
Well, yes and no. So you can actually trace with Windows. So the tracing dialog we showed actually just assembles a command line using the tracer. The tracer is actually a command line from Windows. So of course you can use Windows to trace, but the problem is you can't actually replay it on Linux because Windows replaying engine is kind of their own thing. It's not open source. So there is no way to do that on Linux unless let's say somebody reverse engineer that and make it possible. But I mean that's a lot of work. So I doubt that would actually ever happen. So if you really care about your own security, maybe try to use two Windows virtual machines, one for recording, the other one for replaying.
Yeah, I still don't trust this enough to run the trace on my clean virtual machine that runs Windows because I still don't know. Like, I know
Yeah.
it's just basically a log, right? And it logs like every single operation that occurs. Is that right?
I think now I don't know the details because Microsoft doesn't really say it, but my understanding is when you replay the trace, it is actually emulating the instructions and
Okay.
also considering all of the recorded outputs. But yeah, I mean, don't quote me on that. If you ever get owned by this, don't blame me because you know emulation is also complex. There could be 0 days, but I don't think anybody would be targeting that at least for now.
Yeah, that'd be pretty complex attack chain if it were to be the case.
Yeah.
Yeah, so basically debugger is like the typical WinDebug console that you would have. And then Python, are there callbacks and stuff that you can access using the Python API from the TTD traces? TD
Not
traces.
the TDD trace, but we do have a DBG object. Just type DBG and press enter. You will see there's a debugger object. And if you use autocomplete, you can see all of the methods that you can call on it. So basically, our debugger is also scriptable, just like any other parts of Binary Ninja. Like you can actually headlessly control a debugger to, yes, you can see all of these methods can be called. Um, yeah,
Oh, go
you can
reverse.
every
Nice. Yeah, okay.
yeah, get register value, change register value, which doesn't work in TDD, obviously. And also you can, step forward, backwards, just do all of the typical things. So this is a little bit off topic, but I mean, our debugger API is also very suitable for automating malware analysis. Let's say you have a ton of sample that is somehow similar, and you can write a script to automate, dumping the configuration of it. I have actually seen people do that, but I can't remember whether he published that as a blog or something.
Yeah, stepping, the stack pointer.
Yeah, everything it has everything. Like, I mean, everything you can think of probably.
Okay. And then we have the stack trace window here. So do you guys just use the stack unwinding from WinDebug, or do you have like a custom implementation?
So we do have. So this is mostly built on top of Windows stack trace provided, but we also integrate the static analysis information. So for example, let's say if Windows trace has contains a function with no symbol, but in Binary Ninja, If you already gave it a symbol, then I will use the symbol name here. Let's see if the base thread init function is actually unknown from Winterbug because let's see, it doesn't have the symbol. So it will just be the address of that function, which is not very readable. But if you already did your static analysis, you gave it a name, and I will just use it here.
Right. Okay. Yeah, that's awesome. And then when we're doing the trace debugging, any changes to the original database are saved, correct?
Yes.
And
It
then
used to
go ahead.
everything will be lost, but that is like maybe a year, at least 2 years ago,
Okay.
which is a thing that people complain a lot, and we prioritize that and fixed that.
Okay. Yeah, very nice. And then what was it? What else was I gonna ask? Is it easy to like dump memory from like I guess you could just select it and dump it like you would normally in a Binja
Yeah.
instance, right? Okay, cool.
Yeah.
Yeah, we can mess around with all that stuff.
So
Okay,
you
cool.
haven't showed the coolest thing. Like you can step forward and step
I know,
backward.
I know, I know, I know. Sorry.
Are they
It's,
saving that or something?
okay, so let's do the coolest thing, which is the basically the entire point of of recording a TTD trace, is you have all of these debugger options here, so you can like disconnect, restart, kill the process. You could step into, step over, step return, basically step till return, or like continue till return in something like x64 debug. And then we could change the adapter settings, go backwards. So this would basically just run the sample in reverse, right? Is that correct? And until you hit like a breakpoint or something?
Yes, almost correct, but it's actually not running. I mean, it's replaying the trace.
Or replaying,
Uh,
sorry. Yeah, I need to get my brain wrapped around traces because it's kind of like
yes. I see
okay.
you open two tabs, not two tabs. I mean, not two windows for the same view. They are both showing disassembly. Why wouldn't you just close one of them and make a lot of space for
Or
that?
yes, usually I do this, but I guess we don't really need the high level IL right now. Okay,
You can
so
actually do debugger create stack view. That is my typical. Okay, yeah, this is also helpful as well.
okay, so
So I typically do debugger create stack view. Basically have code and stack side by side. So
like
um,
this,
you could go to menu debugger create stack view.
debugger.
No, that not that one. I mean, you go yes, yes. So these two are slightly different. So we want to integrate the two, but I haven't get to there yet. So this stack view on the right, ideally we should actually also show the concrete value during debugging so that people see the value of these stack variables. But that is a planned feature, and I haven't get to there yet. But I
The con-
usually just show, pardon?
the concrete value being the value contained within that local variable or what have you.
Yes, yes.
But what is
So
it?
there
It
is
doesn't
a
show anything right now.
yes. I mean, I'm just trying to say that is a requested feature, and I plan to do that, but I haven't really get to there. And I actually wanted you to show a different stack view, not this stack view. This is a stack
Okay.
widget. It's not a stack view.
Okay.
Can you close this? Yeah, and also just click debugger, create stack view. Yes. I noticed we do have a little bit of lag here, so it could be
Okay, so the stack view in this case is just like the disassembly, or sorry, like the disassembly view of the stack. Is that correct?
it's just a linear view showing the bytes on the stack.
Or the linear view? Sorry. Yeah, I'm still
Yeah.
getting used to the nomenclature. Okay, so let's mess around with some of this stuff. So if I do you have any suggestions for viewing these bytes in a better way? Or okay, let's try it with some of the stepping stuff, and then we can mess around with the stack view a little bit. But yeah, I am interested in that. So let's so there's a very basic program as we saw earlier, basically just loops. So if I go to the graph view here, we just have our start function here, entry point. This little arrow indicates where we currently are. So if I do a single step, then we can see the little highlight, and then we'll jump to a comparison operation here. That's just checking the value of EBP minus 4 hex, which is our local variable I in this instance. And then if it is greater or equal to then I, then it jumps to the left. And then if it's not, then it will jump to the right here, which goes into these sub functions. So let's step through there. Since we don't have an input yet, it will just go into this function. And then we have a completely new function here that is basically what you saw earlier in the console, which basically just prompts you for a name using this string. And then it writes it to the console using write console A. Then we get input from the console using read console A, and then it returns that value to the previous function. So let's just step through this. Pretty straightforward. But what's really nice is we're not actually running this. This is all just a trace. So if I do like step over, forget process heap, and then look at the value of EAX here, then we can see that this is actually our heap address. So then if we navigate there, this is actually the heap in memory. So within our linear view here. So nothing's actually there right now that we care about. But if we keep stepping here and then we allocate onto the heap using heap alloc, then again in EAX we're going to have our heap allocation offset. So if I pull that up here, we can see that that's that offset there. And then we're going to pass that to, we're getting the standard handles. So these are standard handles for the standard in and standard out within the console. And then I'm going to pass that into ESI. So here we can see again, the string label is showing up in our registers box here because ESI was changed to that string. And then if I keep going here, then we're just going to have a copy that's written to the console. And then the read console, if you will remember that I did enter the test name earlier. So we should see that here. So if I do read console, then we should see that in one of these registers, I believe. So that's variable 8, and then that's moved into EAX, and then we can see that's test. So we're not running this live. This is again a trace, and then we have that test value there. So pretty cool. Say we wanted to see that again. This is kind of a lame example, but we'll go through some cooler examples in just a second here. We can step backwards. So we can go backwards in time, and then we can step over backwards. So say I don't want to go into this call, I could step over backwards and not go into that call. And then we can step backward until return, which I don't really know what that'll do. Would that basically go back until before this function was entered? Is that right?
I believe so. You can try it.
Let's try it, yeah.
It won't work. It's a trace. So even if
Yeah.
you did simply something, you can just go to the very beginning of the trace and then recover everything.
Yeah. So then basically now we're at the point
That,
where,
I mean,
go ahead.
yeah. I mean, this one convenience that you don't have to be fearful of pressing a wrong button and then you have to restart everything actually gives you a lot of, ease of mind. So that could subtly affect your performance as well. I mean, we don't have a study on this, but I just feel like when I do TTD, I'm so relaxed. I'm not fearful of anything. Like I have a trace, so I don't care about whatever it does. I mean, like, so that's also a great thing to have.
Yeah, I agree. Okay, and then let's continue. So we're not at the point in which the test value is entered, but if I just do a step over here, then we can see that value contains test. So basically it reran that trace again, even though we stepped backward out of that function. And then if I continue here, step in, then this is where that Easter egg is checked for. So pretty easy to see what the Easter egg is, 3GG exclamation mark. And then if that is found, then basically we just output this, you found an Easter egg to the console. So this isn't a very good illustrative example just because everything's in plain text. So you could just do static analysis with this. But say, can you actually modify the execution in the trace, or you can just visualize it? Like you can't modify the execution flow like a normal debugger, right?
No, you can't because it's already recorded. So, I mean, there is no chance you can actually modify the execution.
Cool. Yeah, that makes sense.
It's more observing and understanding the behavior of the recorded trace.
Yeah, definitely. Yeah, it's just me getting used to it. So that's super helpful. So, okay, so let's see, where is this comparison operation made here? Yeah, I do compare string A. So I can even set a breakpoint here. What's the easiest way to set a breakpoint?
Press F2.
Okay, F2. And then if I continue here, so I'm just going to hit resume. then we can see that test is being compared here. Well, it's not super easy to see, but that's in our argument here, which is ECX, which is test. And then we can see that the jump is not taken here due to, let's see if a jump equals, then basically we just say the hello name. So we'll basically have the name output earlier that we saw here, and then we'll have, otherwise we'll have the Easter egg string output here. So I should have recorded a trace where we did see the Easter egg or whatever, just to, as a fun example of seeing breakpoints hit, but that's okay. We don't have to kind of beat a dead horse here with this particular example. But then if we want to step until the end here, let's see, step till return, then we're just going to hit our typical while loop again. That is basically checking for the inputs that we were providing from that trace. So really basic example, but pretty cool in TTD. If I go to some other examples here, these might take a little bit longer to record, but I thought they'd be a lot more fun. So I'm just going to discard our changes here. But if we made any changes during our TTD debug session here, then they would be saved. So if I want to say that...
Well, actually, I want to make a clarification here.
Go ahead.
Unfortunately, not all of the changes will be solved. So if you make any changes on things that are backed by analysis database, then it will be saved. But let's say if the malware actually allocates some shellcode on the heap, and that heap is actually not in a range that was originally mapped in the PE, then it will be gone. So this is also a workflow that I have trying to resolve, but it's complex. So, I mean, for now, if you know something is going to be gone after debugging, you better save it manually. Let's say you dump the shellcode for further analysis or something. Right now, it won't actually warn you if that is happening. So, but otherwise, let's see if you change the function name, like what Josh just did, like compare name or something, that will also all be saved in the database.
And the thing I really like is, say we wanted to, I don't know, dump this stack address or these strings on the stack, then I could literally just use the API here. So say we're mid analysis session with this trace, and I want to save those values, then I could just do something like bb.read, right? For if anything in the linear view, I should be able to access. Is that correct? Or
yes,
you are an Easter. Okay, or you found an Easter. So yeah, so basically anything that's available from the typical binary view API within Binary Ninja as well is also accessible during the trace debug session, which is also very nice in my opinion, because I use this API a lot.
So if you want to dump something from linear views, there is actually a easier way to do that. Let's just drag a selection, just randomly drag a selection and right click on it.
Like this? Copy
and
as.
you see there is a menu entry called selection, and you can selection save as.
Oh.
And also you can also adjust the size of the buffer, because in most of the case, let's say the malware decrypts a PE file, you probably know its start and size. So you can actually drag a selection randomly and set its size, and then click the save to and choose a place to dump it to disk. This is what I wrote, and I use it a lot. And I hope people know about that, because this is going to save you. I mean, it's not rocket science, but it will save you a little bit like time. Like you don't have to type anything in the console. You just drag, click, and boom, down.
Yeah, like that. Bad code says, did you say that data allocated in the heap won't be saved? Yeah, that's correct. So basically anything that's not in the Binary Ninja database, once the database is opened, and like how would you describe what's not saved? I know you had a term for it earlier.
So any changes made to a place that is not in the memory map will be discarded. By memory map, I mean not backed by a segment or a section. And this is, I think it's easy to understand, because PE have a few sections, right? And anything other than that, like the stack, the heap, the path, will also all be gone after debugging. I mean, the changes to all of to any of the memory ranges that are not originally present in the PE will be missing after debugging if you do not do anything.
Yeah, yeah, that makes sense. And then Rajnikant said, which we're going to discover is indeed the case in a second here when I open a sample. They said, does this mean that the sample can be unpacked using TTD? And the answer is yes. As long as the unpacking routine is executed during the trace. So obviously there's some unpackers that have some anti-analysis techniques where it'll exit before the trace captures them. Then that wouldn't be captured. But any other time, you've all seen me on stream and recordings and whatever, that I've been able to unpack things in my virtual machine here that doesn't have a ton of hardening. Basically anything that's within that trace we'll be able to capture and dump and unpack. So
Yeah. And also, so I think TTD has a lot of potentials with unpacking. So I don't know what you did on your previous stream. So one of the benefits of using TTD to do unpacking is basically, since I have all of the trace, I don't have a lot of pressure to actually find the correct instruction, correct moment to dump it, because I already have everything. So like if I, for the first try, it's maybe a little bit earlier than the exact point, and maybe for the next try it's later. But I have infinite opportunities to repeat that process, and the trace won't change at all. So I have a lot of upper hands here. And also the other cooler thing, but unfortunately we are probably not going into details today, is TDD actually have a data model which allows you to run queries on it. You can think of this as SQL, or I mean any of the database queries. So for unpacking, we can just write a query or somehow implement a query that selects the bytes that has been first written to and then executed. Now, for those, all of those bytes are self-modifying code. If this query actually returns 0 bytes, which basically means this binary is not self-modifying, which is easier to analyze. But for most of the malware, we believe it's packed, and this query will actually return a list of instructions that has been previously, so the bytes of the instruction has been previously modified. And we can easily find the first of such instruction, and we then dump the sample when that happens. So there is also even an opportunity to automate this unpacking process. I know maybe Sergey from Unpacking is already panicking, but this is the power of TDD.
And then can you, using that query language, could you say like, give me all the instances that virtual alloc was called, etc.?
Yes, of course. They have a query interface called all of the calls, and you can specify all of the functions. And you can not only give one function, you can use wildcard on it. Like say you have virtual alloc ex or whatever. And also you can also get all of the parameters of that function call and put it in a nice table and show it to the user, which is one of the features I'm planning to build natively into BinDNinja so that you can actually browse the trace easier. So, I mean, this is jumping a little bit in the progress, but my view towards TDD is basically in the future, debugging will not be linear. It will become a data science. So you will have a trace, and what you all need to do is basically run queries. Either you write it or rewrite it, because maybe writing the query can be very challenging. But you just run queries on this, and you understand the trace and extract any of the information you're interested in. So that is actually one of my friends described it as TDD is a paradigm shift in debugging. And that is actually a pretty big word, paradigm shift. It's basically you're not actually doing tic-tac-toes with, you're just not, it's actually just bringing debugging to the next level, as one of the blog posts says.
Yeah. Yeah, I think you're right in that respect. How do I get to this query language? New query model or new mode query?
I'm not prepared for that today. So you can actually
Okay. We can do another stream on it.
Yeah. Sorry about that. Because we kind of screwed up the time, so I didn't have time to communicate with Josh on what to cover. But
Yeah.
you can run something really simple. Just say I will send you something on Discord. You can actually run that in Windowbug, in Binary Ninja, you don't have to use Windowbug. You can just open the trace and run that in the debugger console. You don't have to use Windowbug.
Oh, cool. Okay. Oh yeah, because then
Yeah.
I can yeah, I understand what you're saying. So I can run the query from here.
Well, I mean, you can also, yes, you just run it in the debugger console. And maybe you want to close the stack trace widget because it's eating all of the space.
Yeah, if you send me a query, I'll run it. Let me look at chat here. So XOR
Yeah.
Valak, does TTD bug work well for side-loaded DLLs? Think malicious code being run on a side-loaded DLL. Forgive me for if this is already answered. I had to step away for a moment. So I think I know the answer to that question. So basically, side-loading typically is done by abusing legitimate applications that are going to load those DLLs and execute them at runtime. So I think that would obviously be in the trace. Is that right?
It depends. Like, let's say if you realize, if you record malware.exe, but malware.exe injects some shellcode or DLL into explorer.exe, then you wouldn't have that in your trace. But if it's the other way, let's say you recorded explorer.exe, you will actually have access to that. So this is a limitation of TTD, is that you don't see, or better say, a limitation of Windowbug TTD because you don't see all of the things happening on the system. So here is, but remember there are full system TDD solutions as well. Not going to name that for now, but there are full system TDD solutions you can use, basically, and that has a paramount picture of what happens on the entire system. So you can also even debug a driver, let's see.
That's a
Do you
good
want me to
question.
name them, or do you want to not do that?
Yeah, definitely name them.
So there are two solutions that is full system. One of them is called Panda. You can search on GitHub. It's based on QEMU, and it's a research project. Basically, it's a TTD solution, full system. You can run the Windows virtual machine, and all of the things that has been executed will be recorded. And also we have, and also there is a ES reverse from eShard. Basically, it's also similar to Panda. It's a full system record and replay, but it's much more faster. And also, when Binary Ninja has integration with that one as well. So we have, my vision is we integrate with a lot of TDD solutions. Windowbug is one of them. And if you reverse engineer Linux malware, you can use RR from Mozilla, the team behind Firefox browser. And also there is another solution called Undo from undo.io. So that is their company. So there could also be other TDD solutions I cannot remember at this time being. But Windowbug is like sorry, Binary Ninja debugger is like a bridge with all of these backends, we call it, because developing a TDD is a lot of investment, and we don't have all of the resources for that, at least for now. So our solution is basically we take the technology and we build all of things on top of that to help you reverse engineer malware or whatever you're targeting.
Yeah,
Yeah.
that makes sense.
If you run that command, you have to change the address first. So that is something I just copied from a different blog. So that is the two addresses, the start and end of the range, and then that E means all of the executed instruction. So you can actually just set the start to be like 40, to be the start of the start function, and maybe the second address of the address of the return. So and then this query will return all of the instructions that has been executed within this range. Yeah, and also you probably want to close the stack trace. It's eating, yes. You can't read it if you don't have a wide enough. Yeah.
Oh, sweet. This is awesome.
Yeah, yeah. You see all of the instructions that has been executed in this range, which maybe we have a dozen of instructions here, will be returned. And it has all of the information like the event type, thread ID, time. Time is super important. So the time is actually not the time step of that. It's actually an index that uniquely identifies any of the instruction that has been executed. So if you want to rewind to an instruction, you can use the time step, like 1A:51 is, they have a term for that, but I cannot remember. Let's just call it index. So the index for the first instruction is 1A:51. And you can actually later rewind to that instruction directly if you want. And also, so this query is actually querying all of the executed instructions. If you replace the E with R or W, it will give you all of the memory that has been written to or read from the range. But of course, you cannot use this range because these are instructions. They aren't actually written to. But if you use a buffer that has been actually written to, it will be actually written. No, yeah, this query will be empty.
Yes, that's super nice. Yeah, so funny story about Panda is I saw the Panda presentation at Recon. It was a long time ago now. I think it was like
Yeah,
Recon in like 2016 or something.
yeah, 10 years
And
ago probably.
the presenter, what's his name? He's a prof, but he's doing a bunch of offensive AI stuff now, I think. But he basically recorded Spotify playing the Rickroll, and then he did the TTD trace to where he was able to extract the original audio in an MP3 file. So basically, he got around all their DRM stuff by doing a full system trace. So you can do a lot of
Yeah,
interesting things. Not that I advocate piracy,
yeah.
but
That is actually a very typical usage of TDD. Now, of course, if I do that presentation, I will use a ransomware, and just responsible researcher. So, but for analyzing ransomware, especially its crypto system, using TDD is a very good approach because so Windows TDD also has the primitives for taint tracking. So you can do taint analysis, basically trace data flow and understand how our device form, which is pretty far powerful. But I mean, the tooling is not great. So my role or my job is basically taking the technology and build all of the cool things on top of that and keep it to the end user so that folks like you guys can actually benefit from it more directly. You don't have to learn how to run those queries and or learn how to actually do a taint analysis based on the primitives they offered. So as I said, TDD is a very powerful technology, but without proper tooling, it won't unleash the full potential. And it is my mission to just do all of the tooling things for you guys, basically trying to make it more practical and
yeah,
and basically, yeah,
yeah, that's super cool. I'm glad that you're working on this because it's a really good problem to be working on.
yeah.
Hey everyone, thanks so much for checking out the live stream. If you are interested in learning malware analysis with Binary Ninja, please visit training.invokere.com. Thanks so much.
Yeah.
Okay, so we can do a more complex example here. I don't know how long this trace is going to run because it's like a bunch of C++ code, but this was a packed
It should
sample.
be fine. It should be fine. It's like maybe a single digit slowdown. It's like maybe 2x, 3x, or 5x. So you won't feel like it's super slow. But it's of course slower than direct execution, but it's very efficient.
I unpacked this on the stream, so we shouldn't have any problem doing it in the TTD trace. Yeah, so okay, so yeah, this is really good because it has dynamic function resolution. This has shellcode that is eventually called. So this should be a really nice example.
Yeah.
So let's get
So,
into.
so I see in API function resolver. So with TTD, you can actually run a query and get all of the places where it is called and what the returned value is. So you see all of the function pointers that has been returned, and you know what API functions have been resolved by that.
Okay, we got a bunch of questions. So since TDD captures the flow, does it mean that we can somehow use it to defeat control flow obfuscation?
Well, yes and no, I think. Yes means, of course, it has a recorded execution trace, so you can actually follow the flow. But I think control flow obfuscation, the real problem is is for you to understand what is happening. And also there is the problem of code coverage. So tracing will only record the actually recorded instructions, the actual execution flow. So let's say you have a malware and it's a rat, right? It is a and it has a giant switch case. So it has 10 functionalities, but you can only trigger one of them to run, or maybe three of them to run. So you only have these three in the trace. So it doesn't actually magically solve the problem of code coverage, e-malware analysis. But yes, I mean, it does help with analyzing certain control flow obfuscations. And it is sometimes even better than directly debugging that because not only you have a paramount view of that, you can potentially deal with multiple obfuscation at the same time.
Yeah, so basically it would be like solving control flow obfuscation from the view of a debugger, basically seeing where the control flow goes, but not necessarily being able to visualize it and interpret it, how like you would say use automation within Binary Ninja to solve the visualization of that control flow obfuscation, which is like a whole other problem set. But that's kind of how I think about it. Okay, so
Yeah, so I bet you in cases like, if the malware leverages exception-based obfuscation. Now, of course, if you understand it really well, you can actually debug it properly. But that is challenging, right? Because the exception sometimes make the control flow run free. Like how the sample can run free if you don't do the right thing. But for TDD, it's like it doesn't matter. You just see whatever is next instruction executed, and you will be able to understand what has happened.
yeah, record this one. Launching. Okay, I don't know why that finished so fast. Let's see. But it might have exited early, but I don't think it should have because I've definitely unpacked this on this machine. So, but let's see.
I mean, it's not super fast. Like it does take a few seconds, right? So that is just the typical slowdown of TDD recording.
Yeah. Okay, so let's answer a few more questions, and then I'm just going to see if this trace actually worked. So basically, Duncan said this is based on the control flow obfuscation question. Not really best you can do is a guesstimate based on the execution trace. Yeah, exactly. So, but not all blocks are executed. You will not see them in the trace, and they would not be recovered. Yeah, exactly. So Duncan provided a VM Protect virtualization repo, and he said you can see a similar approach for VM Protect there. Okay, yeah, I'll definitely check that out. I think it's also interesting to note that it will be a tax max of 1 year until all malware will have detection for TDD recording, which is extremely easy to detect. These tools are really powerful, but nobody knows about them yet. Once it gets known, it's over. Just like Tiny Tracer.
So I don't think that is super accurate representation of the situation. First of all, of course, malware can target TDD recording, but TDD recording can also adapt. Even before that, let's see, we know malware can leverage tracking and debugging and all of the cool stuff, but I mean, not all of them are actually targeting all of them. It's like if you put yourself into the shoes of a malware developer, they have tons of methods to protect their malware against, right? And maybe they will only target those, let's say, easier ones and also the more visible ones. That is the first aspect. The second aspect is we can also adapt TTD just like how we adapt, debugging and anti-debugging. Right now, the most common detection method is actually trying to find whether those well-known DLLs are in there, but we can actually change the name of DLL and also maybe patch the recorder a little bit to make it also work with that. So, of course, I mean, I think it's going to be another cat and mouse game, but we're having the upper hand probably. I hope so, or better say.
Yeah. Okay, so I think it's always going to be a cat and mouse, especially with like a lot of commodity malware.
Yeah.
I think advanced protectors and stuff will probably be able to detect it, but literally it's if get module handle td record cpu.dll. Yeah, I think that's basically what Xusheng was saying is, but we might get silo hide for td. Yeah, you should create that, Duncan. So then Yeah, if we change the module name to something less more common, it might be harder to detect. But then obviously they can just walk or get proc address on the common TTD
So, I mean,
functions or whatever.
we can actually also inject a anti-debugging module into the recordee, like the process being recorded. So you can actually apply the hooking and also all of the normal anti-debugging techniques on it, right? Let's see, it's detecting the module. Of course, we can change the module name. That is the first way. The other way is actually we can just do regular anti-debugging on it. We can hook the get module handle whatever thing and just filter it, and or just like the X64 debug anti-debugging plugin. I can't remember the name. What is the name of the plugin?
I think it's Silahide is what
Oh yeah,
Duncan
yes.
was talking about.
That one actually can also be injected into the process that is being recorded, so it can actually just get past all of the known anti-debugging techniques. So TDD is not worse, or better said, TDD is not easier to detect than all the other debugging techniques. And yeah, I mean, for now we are using regular debugging, and people and malwares are trying to fuck that, and we can still do debugging. That means we can probably still do TTD, even if people try to target that. But I do agree that maybe in a year or two, some samples will be stopping to work under TDD, and we have to somehow adapt to that. But that is not the end of TDD. It's just like maybe a new era or something like, you know.
Yeah. Duncan's also like doing very advanced things as well. He said another method is to unset the instrumentation callback and it will instantly break the TTD recording. But
Yeah.
I don't know. There's like a million different ways you can basically break it. Internally, the recording actively prevents you from changing things to it. It has DRM, so it would be difficult. Oh, that's annoying.
Yeah. In that case, maybe full system TTD recording will be better because you're recording at a hypervisor level and you only record all of the non-deterministic things at the CPU level. Let's see. Um, so that is a lot less intrusive to Wonderbug's recording. But that then you have to get it around anti-VM or stuff like that. So yeah, there is always a way to screw things up and stop the recording, and but problem is if we can get it harder for the bad guy to do things, I think it's still beneficial.
Yeah, I agree. Okay, so this is a little bit harder to visualize because this is C++. But let's see if we can get some of these values that they're deobfuscating. So again, this is all in a trace. So if we wanted to bring this elsewhere, we could definitely do that. But I think this function just, if I recall correctly. So, okay, so see, like I missed where this EDX value came from. So I can just go backward. Let's see here, into this function to just step over. I still need to get used to this. So if I go step over, okay, we can see that EDX for some reason has this processor revision 5507. But if I go step over backwards and then enter this function, then we can see what they're looking at here. So there's a bunch of these obfuscated strings. I'm pretty sure that this is basically just concatenating these, if I recall, from when I unpack this myself. So this is probably a poor example, but let's take a look here. Yeah, I think if I recall, it was constructing this giant string, but let's convert that.
Do you intend to find out how is the string formed?
Yeah.
You can actually just put a breakpoint on it and rewind back, like put a hardware breakpoint on the string and rewind back so that you will know when is how is the string forming.
So I don't think the only reason I don't know if I can do that right now is because I don't know where the final string is going to be, if that makes sense. But I know I'm like used to regular debugging where we have to worry about catching it in the right place. So I can just like skip ahead here to the bottom. So let's execute till here. And then let's see. Yeah, there's nothing obvious, but and then now we're in this function, and this is the one that was doing the dynamic function resolution. So let's go here and then go here. See, like I missed that call. So let's wait, I don't want to go here. Hold on. Okay, so it just resolved kernel 32. So that this is going to be the address in EAX is kernel 32 in the trace. So this MZ binary in memory is kernel 32. And then we have our dynamic function resolution here. So if I step into this, then we should see this in real time here. So probably better from this perspective. So if we add EAX, then this is going to be the start of the, but we can literally watch it walk the in-memory module for kernel 32 in this while loop through this trace. And then we can watch the hashing function as well if we'd really like. So if we go into one of these guys, then we can see here that the EAX value is acquire SRW lock shared. And then we can walk through the hashing function here. So arg1 is going to be this hash value. And in this instance, it is going to be edx is going to be the hashed value here. So if we just keep jumping over this, we can watch the API being hashed in real time, which is fine. Not real time, in traced time, I guess. And then if I step till return here, then we'll see in EAX, this should map to an actual function. So yeah, one question I was going to ask, here, let's see, there's a whole bunch of chat. eShards products are really amazing. Bad code, is it possible to query for where the program is using some dynamic values and that existed from the trace? Like when you entered test in the original example, could you quickly search to see where the code test is used?
Sure, yeah, you can do that. You can just tint the bytes once the call to read it from the console return, and you have it in the buffer, and you just tint it. There are two ways to do it. First, you can, if you're old school guy, you can put a breakpoint on it, hardware breakpoint on it, and then you resume the execution. And the next time the byte is used, it will break. Now, of course, I said you put a hardware breakpoint, but everything is actually just emulated. So behind the scene, the Wunderbaut engine is actually reviewing all of memory access and find the place that this byte is accessed, right? So it simulates a hardware breakpoint. It's actually not executing. So but it retains this behavior. That is one way to do it. The other way is, I remember they have a way to basically query the place where the byte is read, and you can do some static analysis potentially with Binary Ninja to see where is the content reading to. Let's say it's loading the byte from the memory cell into a register. Let's say it's REX. Then you can also run another query, see what is the next time REX is used and where is the sync. So if let's say for the next time REX syncs into RBX, then basically you can reconstruct a data flow of how the bytes is used. This can be even more powerful than just put in a hardware breakpoint and find the next time it is used. Because if you have a data flow, you can actually have a list of the places where the byte is used instead of just having one. But of course, for this to happen, we will build a tint engine on top of the trace, which is totally doable from an academic point of view. But doing that and create a product on it can be challenging. One of the obstacles I see is path explosion, because maybe a lot of places use the byte test, and you basically I create a data flow, but that data flow is essentially just the whole program. It gives you no information, right? That then wouldn't be really helpful. But suppose let's say the program is not doing crazy things, we can potentially just give you a very good, either we call it tint analysis or data flow tracking, and you can essentially directly know where the byte is used. I think at reverse, as Josh mentioned, I gave a demo to him on how we can put a breakpoint on a string. We don't know how it formed. Let's say we see an interesting string, maybe it's your credit card number, but you don't know where it is coming from, right? You can actually just put a hardware breakpoint on it and resume the execution, but in the backward direction. And then you can find how the byte is forming, how the string is forming, and then you can see where it is coming from. Maybe dumped from your browser, data storage or something.
Yeah, that makes sense. Okay, so say I wanted to see what symbol this maps to. So I know this is probably a Microsoft Windows API, and it's relative to EBP. Do you know of like a good way to do that?
Run this command in Windows. Let me find that for you. So first of all, we should actually, I mean, or better say, I should actually just pull that information from the backend and show it to you, right? So that you know that symbol is there. But I didn't do that because tracking the symbol change can be a daunting task. It is not hard at all to pull the information and present it to you. The problem is to maintain it and always show the up-to-date information.
Yeah, so the reason I ask is because I use that a lot in x64 debug, which is like a big reason I use
You
it.
know that command in Windows to find the nearest symbol?
I used to. I can find the command. Hold
No, I'm already asking ChatGPT.
on. Okay, that's what I was gonna do. I was gonna use cursor, but
I asked what is the command in Windows to find the nearest symbol from an address? It's ln followed by address. Yeah,
ln.
just type ln that address and you will know. If you
Okay.
believe, let's see,
So
rex holds.
and then is there a way it was at right?
So first
Or
of all, I think you are running it in the target window. It's wrong. You should run it in the
oh yeah, you're right.
debugger console. Yeah.
So if I do
Yes, you can use the register name here if you
yeah,
want.
so at EBP minus 0x1c.
I don't think that works because it's
Well,
actually
let's try.
referencing. I mean, there is surely a way to dereference the content out there, but that is not the way to do that.
Yeah, so there's basically
So,
not a straightforward way to get that symbol. If I step into it though, will it resolve the symbol in the stack
well,
trace?
I mean, so move your mouse to the lower right of the window, and there is a CCTV camera there.
Oh yeah.
That is a widget. It's called Debugger Info. Maybe you just want to open that.
Oh cool. Okay, and then nice. What is this? Oh, debugger info. Okay, so then
Yeah,
ln.
you just ln this hex 777DE whatever. You get it. Yeah, you just copy the value and put it after ln and you run it and you have it.
How do I copy that without having to type it out? DE840.
You
Okay,
just you
load
can
resource.
yeah,
Okay,
okay. Yeah. It's
okay,
not as straightforward as I intended it to be, but there is you can do it.
okay. So then the next thing I'm gonna do, I like having the high level IL open. Or wait, this is the stack view. So let's. Anyways, we don't need this right now. So I wanted to see if I step into this, if it'll show it in the stack trace. Kernel 32. Yeah, okay. So that would have been a way faster way to just is like stepping into it and then seeing load resource being called. And then let's see here. So this is the, okay, I'm going to step until return. And then I'm going to kill these because we don't need them. And then there is a deobfuscation routine here that ends in them calling this binary. So kernel 32, virtual alloc. But let's step through it, shall we? So I'm not cheating by doing static analysis.
Mm-hmm.
But yeah, I think this is the mapping routine, and then this is the original entry point that's called. So let's go back here. So malware load DLL. I think it's a DLL. It might just be a normal portal executable. It doesn't really matter. And then let's see. So just to kind of illustrate why this is so powerful is like as we're debugging and then there's these like new executables loaded, we can just continue on with our analysis and then like dump them to disk if we want. So we don't really have to worry about, I actually don't even know where in the trace I am right now. So I might step forward. Okay, so this is where the trace ended here. So let's restart this. Tumpus said POI does the actual dereference. So pointer.
Oh yeah, PY. Yeah, okay.
Step
It's
this.
such a shame to forget about that. But
I
that is
know.
also the reason why we integrate Windows Debugger with Finding Ninja to basically help you forget about all of those.
Yeah. Okay, so I'm going to set a breakpoint after the resource is loaded. So here, and then let's do launch again. And then we want TTD with our trace. Okay, now we're back in business. So What's also really nice about the TTD stuff is you don't really have to worry about like rebasing your binary ninja instance. It'll just go straight to the correct ASLR mapping in memory and all this stuff. So a lot of advantages.
To rebase it for the first time, but then in later iterations, it will also all remain the same. Like the first time, maybe you need to rebase it, but later ones are guaranteed to be the same.
Yeah. Okay, so EAX. This might also be related to the deobfuscation. Heap alloc. Okay, but we don't really have to worry about this stuff because basically we could just get down to, let's see what this ECX call is here. And then we can do our trick from before where I could see where this is leading to. So see how this is a address outside of our current module. So let's navigate there. And then we can see that this is in-memory shellcode that's performing the load.
Yeah.
Okay, so what's like really cool about having everything in this trace is that not only do we have the shellcode that was just loaded in the trace, but then we can visualize that in the high-level intermediate language. So like usually what I would have to do is I would have x64 debug open. I would get to this point, I would dump the shellcode, and then I would put that in binary ninja. But having this trace, I can like get rid of all those steps at once by just doing this all from the trace itself. And then here we could see that, okay, there's a whole bunch of functions that are called by the shellcode. I think this is just doing the loading if I remember correctly. But as we navigate throughout this shellcode, it's also populated by Binja, or not populated, but it's analyzed by Binja, and then it makes more markups for us, which is cool. And then, so yeah, we can step into this shellcode more and then see exactly what's being done here. So this call is this function. So then if I do ln 490, oh, is that that might be shellcode. Let's see. Jump. Is this
you run it into the target window again.
Oh,
sorry.
crap. Sorry. That's my bad. Okay, get user default LCID. So this might actually be the original malware. We might be at the original entry point here. So let's see what's an easy way to do that in WinDebug. Yeah. This is the original code. So I missed it from being in an unmapped state into a map state. So if we go backwards, then we could probably find where this gets mapped. So what's the best way to do that? But yeah, here's the unpacked binary. And then if I look at this address, I think it's bang address with this. Why don't you have the symbols? .sympath. Okay. And then could not find, weird. But if I go to this, okay, if I get out of single function view, I should just be able to navigate to the start of this, which is also really nice. So let's get out of single function view, same with here. And then if we scroll to the top of this memory allocation, then we should see a PE header. PE, or wait, I went to like the very, very top.
Yeah.
So there's probably like a million better ways to do this. I just want the top of the allocation.
If you want to find the nearest symbol.
No, but I don't want the symbol. I wanted the just the start of this memory region, if that makes sense.
Yeah, there is a command for that, yes. But I cannot remember.
I think it's bang address, but it says there's no mapping at that address. Hold on, let me search that real quick. So find.
Yeah, it is actually bang address, but maybe it doesn't work in TDD. That could be a WinDebug bug.
VA dump, maybe.
Yeah, ChatGPT is also telling me that, but I'm not sure whether it works.
Okay. Oh, I don't have the extension. How can I do this without an extension?
What I'm trying to do.
Address. I just wanted the start of this memory region. So you guys don't pull the memory map or anything, right?
Yes. Oh, so you are trying to find the start of the PE.
Yeah, exactly. Of the mapped, this is the mapped portable executable that was unpacked using the TTD trace.
How about just screwing up and be lucky?
I know, but can we search the memory map with the binary ninja API?
Not, not during debugging because we don't have the memory map, so you can't search. I mean,
I know a better way to do this though, because I can just go back and find where the allocation was made.
yeah. I mean, there is a ton of way to do that, but we're just not really prepared for improvising that.
Yes,
Yeah.
I didn't do a ton of preparation kind of on purpose because
I think it's not a big deal. I can leave that as an exercise for the interested viewer.
I recall lm-a doing something like that. Tempest says, how do I go forward? Copy address lm-a unknown option dash. That didn't work either. That's okay. We can just basically go back to where this allocation was made. So they're walking the process environment block. So again, this is all super nice stuff in Binja where it basically is finding the address of entry point using these offsets. So if I basically just get the, I think this is where the allocation would be made, virtual alloc, load library. This is building the import address table, I think. But if I just get like this address, and the super cool thing about TTD is I can just set a breakpoint there and then I can go backwards to there. And then now I should see in that call.
And you need to step over that call.
Yeah.
To see the return value of that.
Okay, yeah, so you're right. It's like 151, blah, blah, whatever. And then...
Just be lucky. I mean, like...
And then if I want to dump this, what's like the best way?
Do you know its size?
No.
The virtual alloc probably has the size.
How do I get the... I would have to reanalyze this with Binja to get the portable executable attributes, right?
Pardon?
I would have to reanalyze, like, you know how at the beginning of the analysis, when you scroll to the very top, it shows all the portable executable attributes, or not attributes, but the fields populated in the structs.
Dump this to a file and load the new file into Binja to get that to happen. It won't actually do that. Yeah.
So can I? I'm just trying to think of what else. So if I do bv.read, and then I just give it like a giant buffer, it should just work, right?
It will fail. It will succeed or fail. I don't actually know. Let me try it.
Okay, let's try it.
Yeah. So from watching this stream, I think we should really try to prioritize the issue of reading the memory region information from the backend. What?
Why is it saying
syntax?
Oh, I'm in the wrong console.
Okay.
Again.
Yeah.
A lot of this is user errors.
No, not necessarily. I mean, we could improve that.
There we go. That's
you
nice.
have 20x. Okay. Yeah.
Okay, that worked. So it like it'll just give me a bunch of zero padding at the end. But so let's dump this to a file. This is mapped, so let's just call it mapped PE. And then let's just do this in temp or something. And of course, Windows is annoying and I have to escape these things. Right. Binary. Did I do that all right? And then f.write mapped PE. So that would work that way. And then I should be able to get it before it actually gets mapped. So I think this is the deobfuscation routine. So it's just like a basic XOR.
Mm-hmm.
So let's, again, I'm going to set a breakpoint here, and then I'm going to go backwards in time to get to this start of the trace. So I'm going to go backwards, and then I'm going to step over this. So it finishes the deobfuscation routine. Wait, what just happened there? Wait, so I'm going to go backwards. I'll step in, and let's just see if this is indeed XORing the original bytes. So yeah, so this is, so see the M and then Z. So yeah, this is deobfuscating the portable executable in memory. And then if we go, let's see, step out, then this should be in EAX or something. Or was it was an argument that was provided, EDX. It'll be passed as an argument here, so we could just get it there. And ECX. Okay, and then this is the start of the MZ header. So then now I can just do copy address, bv.read. I don't know why I want to make it a string. And then hopefully that's the full thing, but we'll do unmapped PE. And then we'll do f open. We'll just put it in the same spot so I don't have to get that temp path again. Unmapped PE.bin, wb f.write, unmapped PE. Like that. And then let's open that in Binja. Let's see, where did that write to though?
It's in your current working directory of findninja.exe.
Okay, so I'm just gonna write it to the correct path here. So like this, do unmapped, and then I'll write it there. And that was on the heap, so it's probably gonna have a bunch of stuff in it that we don't need, but that's okay. Binja will just parse the relevant stuff. I can also clean it up with Silo, which is like a little trick that I use.
Yeah.
And we'll do unmapped, and then there we go. So this is the unpacked portable executable that is unmapped that we just recovered using time travel debugging. So pretty cool. And yeah, if we wanted to step through this guy as well, this has a bunch of anti-analysis. So I wanted to see if this was going to cause any problems for us on this VM. And then I wanted to see if it would exit early. And then we could use the TTD for anti-analysis stuff, but we don't really have to do that because I know we've been on almost an hour here. Or sorry, way more than that, almost 2 hours.
Yeah.
How are you doing for time? Or is it pretty late there?
I'm good.
Okay, cool.
Yeah, I will send you my bill with the hourly rate after this, so you don't have to worry about that.
Sounds good.
I will be properly compensated for, and that's a joke.
Yeah. Okay, let's check out what else do we got
Yeah.
here.
Is there any questions from the viewers? Because we have been talking for a while, and maybe people are already having some questions.
Yeah, do you guys have any questions? Guys, gals, folks. And then now we could do a trace of this unmapped PE too, if we didn't want to debug it from memory here. No? Everybody's hanging out? All right, let's continue on here. I think there's still quite a bit we can try. I want to see if we hit any of those anti-analysis checks in this, because there's a whole bunch of examples of that. Let's see if we can find them.
So if we do a TTD tracing of the sample and it exits early, so you can actually just go to the very end of the trace, and it will be in NT terminate process, and you can see from the backtrace where is it called, because normally when the process wants to earn early, it will call this call itself, so you can see where terminate process is called, and then you can see what is actually leading to that, and you can deal with that.
Yeah, so let's try that. I don't know if we'll actually hit one of those, but why not give that a try? I think this actually checks for specific files. So I think that would be something we can replicate if we don't hit any of the actual anti-analysis checks. So let's see here. Okay, yeah, let's just run a trace on this. Let me rename it to like .exe. And then I'll reopen that from here. Open. Oh wait, .exe now. And I'm pretty sure it's a.
I don't think you have to change the name. I don't think you have to change the name.
Oh, with the trace, with WinDebug.
Yeah, I don't think you have to do that.
Okay.
I think so, because the create process APIs are like smart, so you don't have to have a proper, .exe anything. But anyways, it doesn't matter.
So yeah, I'll record the trace now with this new binary. Okay, that seemed to be really fast as well. So let's see what we got here for launching it, and then we'll do debug TTD, and then we'll get the trace. Then we'll do a launch. Okay, there we go. And then, so yeah, we can see, should we just see, oh, cool. So we already hit an exit process right away.
We have the wrong language, right?
Let's see. Start over.
Where?
Hold on, I'm just going to restart it. Okay, into EAX. And then let's step out of this because I don't want to go through the API. Okay, so then our EAX value is this 529250. It should pass this, but maybe not this check. Oh yeah, so it is hitting the anti-analysis check. So let's step into this function, or better yet, let's go from the end. So this is a really cool feature. So let's do, so what's the best way to get to the end of the trace? Just hit play, right? Until it exits?
I mean, you can do a step return to go out of the function and rewind the instruction back exactly. Or you can put a breakpoint at the return instruction. Both works.
But I want to get to like the end where it exits, basically. So I'll just hit resume, right?
Well, I mean, you go to the next instruction after the function and you rewind, you do a step into backwards.
Okay. So let's go to the end here. So I was hitting the exit process. So let's just set a breakpoint there, for example.
You might want to work with the disassembly because the high level
it sets like 3 breakpoints.
Yeah, if you work on the disassembly, it might be better.
Okay, and then we hit exit process, and then if I do step into backwards, right? That's probably the best.
Yeah.
And then we hit this jump not equals, and if we go this one.
Yeah, you will find exactly how it exits from this function.
So let's keep going. Oh yeah, cool. So, I don't know where I am here. Step backward, step over. Let's do this one. Okay, so I screwed that up. Hold on. But yeah, it's hitting the VMware check here. So I just saw that. So if I go to this VMware check and then set a breakpoint on this call, then we hit here. And if I step into this call here, I actually can't remember what this function is. This is a Windows API, I believe, that we're in right now.
Yeah, probably.
Let me see with the ln, or let me see the stack trace.
I could really.
Yeah, it's string and string IW. So, and then if we look at the location that I got the string from, then now it's showing string and string IW from the HLIL. So I should have looked at that before.
Yeah.
Then we could see that the string that's being compared with this string and string is this PSZ string attribute. Oh no, wait, that's the one being compared. Let's see the.
So there is actually a plugin, or well, not actually a plugin. So well, there is a plugin called what is the plugin that shows the coverage from a trace?
Oh, like Lighthouse?
Oh yeah, Lighthouse. So one of our user has written a blog that basically you can actually export all of the instructions from a TDD trace and somehow convert it to a format that Lighthouse understands. So you can actually see the coverage of the function. So for your situation, like we earlier need to figure out where it fails from the function. If we have the coverage information, that is also a good way to visualize that. And also that is potentially useful in many other situations as well. So TTD has all of the instructions, and of course, that means it has the address of the instruction, right? So basically the user has written a script to dump all of the address of the instructions, then give it to Lighthouse, and then just benefit.
Yeah, I'll see if I can find that blog after this, because this would be a perfect example for that. So just to recap for our viewers, I'm not sure if you all realize what I just found, but basically, so this piece of malware, so we basically unpack the binary using TTD and then dump that to disk using the Binary Ninja API. Once we open that binary, I did another trace with this piece of malware, which has a bunch of anti-analysis techniques, and then I found that it is finding my virtual machine using this enumerate display devices API, and then it's seeing that that device name contains the term VMware. Not only were we able to dump the unpacked PE, but then we are also able to see that our virtual machine is being detected using this particular technique. So I have two options here now. I could basically patch out this particular check. Like if I wanted to in Binary Ninja, I could patch this to say something else to bypass this anti-analysis check. Anyways, we don't really have to do that on stream, but that is one option I could do, is patch out this particular string to say something other than VMware and then bypass this particular check. But there's a million other checks that this piece of malware is doing, so we could highly likely hit another one of these. But really good way to quickly analyze the sample and see, okay, what do I need to put in place on my VM in order to harden it further to run the sample fully dynamically or what have you. So really cool.
Yeah.
Yeah. Chris Bagg asked, do you have a link to the blog post for converting it to Lighthouse? And then
Search for next level debugging binary ninja.
I think
next level.
I think Duncan might have found it. Is it Camille? TTD bindings example coverage. I can't pull it up on Xusheng. Can only see my Windows VM right now, but let's see if
I will send it on Discord, Josh.
Yeah, that'd be great.
Sorry. The link to the blog post I was referring to.
Okay, I'll throw this in chat.
Logic, and so one thing I like about his blog post is he actually proposed a workflow that I even didn't think about as the developer of this thing. So people are being creative and also creating some usage scenarios that I wasn't originally aware of, which is great.
Yeah, I want to see opening the target trace. Yeah, I don't have to do this all on the stream, but maybe this is something I can do for next stream. I think that would be really fun.
And also what he has done in that blog post is something I plan to integrate into Binary Ninja directly. So in the future, maybe you can just press a button, just like how you installed WinDebug/TDD. Like it's all automated and you just, perfect.
Oh, he's using BN Cove for the not Spotlight, I don't think. But yeah, this is really cool. And then transfer highlights, deconstructing ping. So yeah, I'd want to see this with malware. I think that'd be super cool. Yeah, awesome. Okay, cool. Yeah, so the anti-analysis stuff was kind of what I wanted to do last. Is there anything else you wanted to go over today, Xusheng?
Nope. I mean, you can just go over whatever you want to. Oh, you're saying you're good now, right? And is there anything I want to cover? Okay. Yeah, I don't have anything at this moment. But if we want to do a second stream, maybe I can actually hack up something. Like I said, the way to automate the unpacking process, which I actually previously did, and I told you about it in private, but I haven't really, prepared the material to go over that. But maybe in the next stream we can still deal with this sample, but somehow automate the process of finding the correct place to dump. That would be cool.
Yeah, I think if we could, not only like find queries for common unpacking APIs and then maybe write some automation within the debugger to check those memory address allocation locations or what have you. TTD reminds me of the Tenet movie going forward and backwards in time. Yeah, totally. It's like Sands of Time, like Prince of Persia stuff too. A lot of good sci-fi / fantasy analogies. But TDD is super cool. We could probably wrap up there. So thanks so much, Xusheng, for joining us. I know it's definitely late your time, so I really appreciate you coming on, especially last minute. To give you all context, I basically just pinged Xusheng last night and I was like, hey, I think I'm going to do this stream tomorrow. Do you want to join? So very kind of him to step in at the last minute. And even we both didn't really prepare a ton. I just had some ideas for things that we could do live, but it's kind of better that way because it's not pre-baked. You could see me struggling through the process as I learn how to use all these different new tools. But yeah, TDD definitely seems extremely powerful and it's well integrated into Binary Ninja. So you should all try using it today because it's basically a one-click install. And then obviously you want to run the malware that's performing the trace with WinDebug on a isolated virtual machine so you're not infecting yourself or whatever. But once you have the trace, I don't know, maybe don't take this verbatim, but I'm pretty sure you could run this elsewhere without having to worry about being infected with the emulated instructions in WinDebug. So if that is indeed the case, then I think that's super powerful technology. I'm really interested in looking at these query languages closer because if you could just take a trace and then query out where binaries are being unpacked, that would be a super fast workflow. Obviously, you're having to take into account, as I mentioned earlier, that there's scenarios where you might have anti-analysis anti-analysis in the unpacker, but regardless, still really cool, because if you have the trace with the anti-analysis technique, then you can do the second thing that we did and seeing where it exits, right? So yeah, super powerful technology. Really appreciate all your work on Binary Ninja and integrating the WinDebug TTD stuff and all the other stuff that you've done. So, and again, thank you for coming on. So
Yeah, thank you, Josh. It's my honor to share with all of the viewers on some of my recent work. And yeah, it's a fantastic opportunity to show off. Thank you.
yeah, thanks so much. Very cool. I'm going to kill the stream, but thanks everybody for joining. If I don't talk to you, then you can hop in our Discord. If you don't have the link, let me just throw up a link here. But yeah, really appreciate y'all hanging out, and we'll talk soon. And take care, Xusheng.
Yep, see you.